Here we are once again. It's Natural Science 116 video lecture. Natural Science 116 video lecture 6, and we'll start with some announcements. Okay, so the first announcement has to do with the exam, which will be returned this week sometime. And should be no problem with that. Okay, I already looked them over, they look pretty good. So yeah, we have that. And notes and homework is my next point here. And we want to always turn in some good notes following the lecture. So this is the lecture for Tuesday, and we'd want to have those notes in by Thursday, and so forth. So also the video lecture 6, that means we have 6th, 7th, 8th, 9th, and 10th. We're going to have 10 lectures all together. So we're really running out of time, have so much left to talk about. And don't worry though, I know how to do this. Yeah, so what do we have to talk about? Electricity and magnetism. Before we get there, I do want to discuss one more thing about the heat engine, namely refrigeration. It seems like the opposite of a heat engine, but it's an interesting topic. So I'm going to put a few facts up here, going back to the heat engine, and then we'll move on into electricity and magnetism. And I'll put down a number of words that you can look things up. You can make pictures, find pictures and put them in your book. That was my last point here, your book. So we always want to get some nice images of all these things we're talking about. Okay, so before we're done with thermal physics, I just want to mention one more thing, and that is refrigeration. That's definitely something we should have some understanding about. So first I reviewed the heat engine by just reviewing that schematic diagram that we had, and we'll put the heat engine over here and the refrigeration over here, and then we'll just have one board for it. Okay. So yeah, our heat engine, as you recall, we had a high temperature reservoir. Some heat went into the engine, which kicked out the work that we wanted, but there was also exhaust. So there was QH, QC to the low temperature reservoir. That was our schematic diagram that covered all of the heat engines. And there was the efficiency, and that was E is equal to the work divided by, so the work out divided by the heat input, and since both are energies, it's dimensionless, less than or equal to 1. And then there was the Carnot efficiency, 1 minus TC over TH. Okay, so that's the heat engine, and the principle here behind all of this is that energy flows from higher to lower temperatures. That's my TH here, my TC here, and my Q. So that's that cartoon. Okay, so that's the really abstract summary of the heat engine discussion. So there's a thing called a heat pump, and there's one in every household because a refrigerator is a heat pump, and you wonder, what does that have to do with a heat engine? Well, if you stand in front of the refrigerator, sometimes you feel some warm air coming out the bottom. There's a little hint. Okay, heat pump, and I'm just going to write refrigeration. Now, the interesting thing about the heat pump, and first of all, you could say, well, with the refrigerator, we're taking something cold like a tray of water and turning it into ice. So is it not somehow reversing this law here? Okay. But with the heat pump, what we can do for its schematic is literally reverse the direction of the arrows on this thing. Okay. And remember, this was based on conservation of energy and increase of entropy. And if we reverse the arrows, those two ingredients are not actually going to change. Particularly at first, the conservation of energy is still maintained. So let me go ahead and just draw the schematic and reverse the arrows. Okay, so there, what we're doing is we're putting work in. This is why we have to plug our refrigerator in, okay? And it has an electric pump inside, electric motor. So we have to plug the refrigerator in. So we're bringing some work in here. There's the engine that's doing that work. And it's taking energy from the low temperature reservoir into the high temperature reservoir. So just reversing those arrows doesn't change conservation of energy. So this is legitimate. Now, the way this works, take a little longer to explain. And I'm gonna leave that for you guys to look up and get a nice diagram of this. Just the words heat pump. I'll give you a tip of what to look for. So refrigeration, heat pump. Instead of the efficiency, what we have is the coefficient of performance. Coefficient of performance. Okay, can't read that, but I'm saying it. Coefficient of performance. Coefficient of performance. And what that is literally the inverse of this. It's namely how much energy can you bring up to the high temperature reservoir for how much work you put in. Okay, so the coefficient of performance is the inverse of the efficiency. And so the maximum coefficient of performance is actually the inverse of the Carnot efficiency, okay, which is very interesting in its own right. I'm just gonna leave this here. So look this up. You'll definitely see this diagram. See if you can get some explanations of how a refrigerator works. Well, I can't. You know, an old-fashioned refrigerator had coils on the outside and coils on the inside, an expansion valve, and some kind of a pump that you plug into the wall. And so what you end up with is a compressor that heats a fluid in these coils hot enough to radiate out to the outside. And with the expansion valve, the fluid inside the coils inside the refrigerator is that fluid is so cold that you get energy flowing from your food, say, to those coils. So look that up. That's pretty interesting, and it definitely fits in with our thermal physics. I want you to at least have seen this and have a look at it and get something good on that, put it in your book. So what are the topics? This we know about. So you're looking for the word heat pump. You're looking for coefficient of performance, and it has to do with refrigeration. Okay? So that completes our thermal physics discussion. And then from here on out, we're going to talk about a number of things. We need electricity and magnetism. We need motors and things. We need to talk about solar energy, and it all has to fit in with our logical framework. So that's my next task. Okay, so you have this, that's part of your homework assignment. If you get some good stuff, lay it out and, print it out, lay it out, and take a picture of it and send it in with your notes. Be interesting to see what you find here. Something that's nice and convincing. Good, so I'm gonna erase this and move on to a little outline now of what we're planning to talk about for the rest of the semester. Okay. So here we have these 5 lectures, including the present one, the current one left, and the last one has to be some amount of review, so we have quite a bit to do here. Let me outline this. We've made it all the way through heat engines, all the energy stuff before that. So now we need electricity and magnetism. might think they're separate topics, but they go together. Okay. We'll start with electricity and magnetism. If you remember our big cartoon for the hydropower, that one we could fill the entire board with, and we could include all the electrical transmission lines, transformer substations, you know, everything up to our residential energy use. We could introduce, you know, the sun, solar energy, panels, everything. We could fill that cartoon up, and maybe I'll do it later sometime, with the entire semester's worth of discussion of energy, short of those satellite orbits. Okay, they wouldn't fit in there somewhere, but otherwise everything would be there. Okay, so we need this electricity and magnetism discussion in order to be able to talk about the grid, the electrical grid that we're all hooked up to. It's what makes our whole civilization run. And then we want to extend the discussion into solar power, which we've already mentioned. The water cycle is solar driven, so we really have to come in there with a little more technical understanding. And I would even put in wind. That's kind of a fashionable thing. But wind energy is actually also solar energy, because it's convection currents produced by the difference in temperatures, and those differences in temperatures come about because of the solar radiation. Okay. So everything that we do is going to tie together completely. And yeah, we don't have that many lectures left to talk about it. I usually do quite a bit more because we wanted to build a little electric motor, right? We had ambitions for this. We're gonna have to move a little faster, but not to worry. Still a lot of good material to come. Okay, let's see how we're pacing this on the clock. As you know, okay, great. These videos are all no edit, one take, so we just have to make our way through there. Okay, so electricity and magnetism all being tied into the energy concept. So we will begin this topic here with what's called electrostatics, or static electricity. And everybody has some experience of that. When you pull the clothes out of the dryer, you have all kind of crackling and things holding together and so forth. That's exactly static electricity. You know, when Benjamin Franklin took the electricity from the lightning out of the sky, stored it in a Leyden jar, he was also dealing with static electricity. So there's a whole wealth of little demonstrations. I'm going to keep this very brief, but just to show that there is an electrical interaction, or a new interaction. This is the static electricity type. So you can look this kind of thing up too and maybe get some images, but here's the friction, and that needle moving shows that there is a force, there's an interaction. Okay. And we learned that it's an electrostatic interaction. Okay, that's really enough. If you were here, you could even hear a little bit of crackling, and if I discharge this thing, there's a little crackling too. So all we need to get out of this is that there are these phenomena. Because this needle, this thing here turned, that's enough to know that there was a force, okay? Enough to know that there was a force. And these aren't ordinary mechanical phenomena, little sparks involved. That's all I'm going to show you for these, although there's a whole wealth of electrostatic demos. So static electricity, that's something to look up, get some images and some ideas and some discussion of that, okay? Another thing that's learned about it is there are two types. And we say there is positive and negative electric charge. Okay, so positive and negative charge. You know, they could have called them hot and cold, or A and B, or whatever they wanted to. I think it was Benjamin Franklin who came up with the idea of just calling them positive and negative. The association with electrons and protons, you can look that up as well. We're not going to have to really deal with that. So we've got positive and negative charge, and there is an interaction. Say there's an interaction, I just mean there's a force. And I just demonstrated that force. Okay. So we've got an interaction. Here, let's write that out. Let's make sure we're getting this down systematically. So let's see, what do we have here? We have static electricity, and I'll just write here phenomena that you're aware of. Everything having to do with static cling and sparks and walking across the carpet and so forth. Pulling off a sweater, you feel the static phenomena. But there are two types, positive and negative charges. Positive, negative. It turns out, but this wasn't known for quite a while, that the positive charge is what the proton has, which is an elementary particle, and the negative charge is what the electron has. Okay. Also an elementary particle. But what we want next is to discuss this interaction. Okay. So that was 1, and point 2 here, I'll call this the electrostatic interaction. There are nice demonstrations of this. In fact, let's put it down here as a vocabulary, something to look up for really dramatic electrostatic effects. Look up the van der Waals generator. We have one here, makes sparks and noise, but I'm not going to show it right now. Look it up, you can probably see some nice demonstrations of that. Okay, so put that in your book as well. Okay, but now we're over to the electrostatic interaction. And of course that means the force. And we know about forces. What we have is that unlike charges of these positive and negative charges attract, and like charges repel. Like charges repel. Okay. So for example, you have a plus and a minus, and they're going to be attracted towards each other. There's a force of attraction. You would have to exert a force to hold them apart. That's what we're saying here. Like charges repel. So for example, if you had a plus and a plus, then they would be forced apart. Okay. So the point is that there is a force. Now, why did I bring this demo object here? This is all I'm going to have for you besides pictures on the board. So this is what's called a capacitor, but what you can imagine is that I am able to get positive charges on one side and negative charges on the other. Okay. And then if there were not enough friction, these things would come together. Okay, that's the idea. If I had positive on one side, negative on the other is the force of attraction. Okay. And in fact, it's possible to do that. Okay. Now, what's the point of this? Because this is a class about energy. Okay. So we have positive on one side, negative on the other. There's a force of attraction. What happens if I pull apart on it? We know that I've done work. I'm pulling apart. It's as though I had pulled on a spring, right? I pulled them apart. And if I've done work on them and left it here, then we could say, yep, I've stored some work. Okay, so I started here, some positive and some negative on, pulled them apart. Now I've done some work. I've stored some work, means I've stored some energy, electrical potential energy. So that's my whole point on this. Now these things you can imagine, you got the pluses, you got the minuses, pulled it apart, there's energy stored there. Put it, wrap it up so you can't see what's inside, and then you have some storage of energy. Okay, so that's the whole point, and that's how we make contact with the energy concept. Didn't take very long, okay, because we know about force and work, and then we have energy right next. So that's the point two. You got the electrostatic interaction. Unlike charges attract, like charges repel. You can collect some unlike charges, pull them apart. There you go, you got some energy. So I'll tell you what that is again. It's called a capacitor, and you can look that up as well. Possibly get some images. So point three, the capacitor, charge separation, and that gives us stored work. So in principle, if there's charge separation, there's energy. So I have this capacitor here, and the symbol for it is just these two plates with wires coming out the side. Capacitor, and the point is it has stored work. Or we could have a battery. I'm not even going to try to draw that capacitor, but a battery I can draw, right? First of all, the symbol for a battery is that we have a longer and a shorter plate here instead of equal lengths. But everybody has seen, say, you've got a D cell. I'll write D there, there's a battery. And although it's not the principle of a capacitor, it still has part of the essential property that we're talking about. Based on a chemical property, there's going to be stored work in there as well. Okay, so this side will be labeled with a plus, this side will be labeled with a minus. Okay, so this was just the principle of it. Battery does the same thing. We have stored work, and we know that that's energy. Okay, so my next point is to bring in the some terminology that you actually heard. So that was 3, so 4, we have electric charge. We're going to use the letter Q, and the unit of it is the coulomb. I'm going to ditch the C down here for capacitance because we're not going there. The unit of electric charge is the coulomb. Okay, so unit of electric charge. Okay, this is quickly going to come into familiar territory. The unit of electric charge is the coulomb. Just as a piece of information, 1 electron or proton charge equals, minus or plus 1.6 times 10 to the minus 19 coulombs. Okay, so a coulomb is quite a bit of electrons, a high number. So there's so many electrons carrying charge around that we can often think of the movement of the electrical charges as the movement of a fluid, okay? Because there's so many in any given volume of, say, a wire or something like that. Okay, but the main thing we learned here, we're going to call this Q, and the unit of electron charge, the unit of electric charge is called the coulomb. So this is the first time we have a new unit in quite a while. It's always just been kilograms, meters, and seconds up to now. Now we have the coulomb. Okay, my fifth point is that the work here now, energy. So my W represents the energy for work is equal to Q, the charge, times delta V. And now I can talk about this thing again. It's got charge on both sides and it's separated. So the Q represents the amount of charge, plus and minus, and the delta V represents the separation. And this delta V is the voltage, okay? So here we have energy, here we have charge, here we have voltage. So charge times voltage gives us energy. So this delta V, and I'm always going to write it as a delta and not just as a V alone. This delta V is the voltage. Okay. So that's how much energy is stored in this device I was talking about, which we're going to take as our basic energy storage device. Charge separation, because we did the work on it. You know, we can say we did the separation ourselves. We separated it, we did the work. There it is, Q delta V, and that's how many volts, okay? Good. So this is crucial. Yeah, we can only go through electricity this rapidly because we've had all this background in energy already. Otherwise, this would be much, much too fast, okay? But we're already, you know, work, charge, voltage. So we're in good shape here to keep on going. Okay, so what comes next? 6, I'm going to talk about electric current. And electric current is charges, electric charges in motion. And I'm going to draw a circuit. So let's imagine we have that battery here. And I'll say delta V is equal to 12 volts. For example, that would be a car battery. Delta V is equal to 12 volts. Okay, we've got a car battery there. Charges in motion. Actually, let me make sure that we're seeing the bottom of the board here. Yes, we are. Excellent. Okay. So this is our symbol for the battery or the capacitor. We can take them interchangeably. And the idea is if you connect a wire in a loop, you're going to get a circuit. You're going to get a current flow, and if you get the current to flow through something, you'll get an effect. So here's the symbol and here's the drawing right after it. The symbol is that the current flows through a resistor and it goes from plus to minus. So there's the direction, and the current is called I. So it's a charge in motion, or charge is in motion going through a resistor. If I were to draw a picture of this, suppose we had that battery I was talking about. We hooked a wire up to here and we went to a little light bulb. In fact, let's not draw it too small. So let's have a light bulb here. There's the shell of an incandescent bulb. And you have to hook the wires up like this. If you have something like this at home, try it out. With wires, you go down to the base and you go to the side here, okay? And what's going on inside is there's a thin wire. You need incandescent bulbs to see this. There's a thin wire that's actually getting very hot, it's glowing, and it's giving off light. We'll draw a little light here. Okay. Yeah, so there's a picture, there's the symbolic form. I'll just call this our D cell. Still have current going through the light bulb, giving off light. Okay, and more importantly, actually giving off heat. These light bulbs get hot. So there's charges in motion, and let's write here that we have a circuit. Charges in motion. So current I is equal to Q over T. So the units is equal to the units of Q over T is equal to Coulomb per second is equal to the ampere. Okay, the amp, you've heard about amps before, right there. Okay, so now let's go back to this energy formula. So yeah, this is an important set of pictures here. We've got charges in motion, they're in the wires, those are wires, light bulb, battery. Okay, the basic circuit that everybody's seen in some form or other. By the way, when you flick a switch, all you're doing is interrupting this wire. You're putting a break in the wire, and so we actually indicate a switch like this. Means if I flip the switch closed, then I complete the circuit. If I open the switch, that means the electrons can't flow, electricity can't flow, and therefore the light goes off. Okay, so there's actually the symbol for a switch as well. Keep the light on right now, okay? Good, so you've got that. Okay, I want to get back to this formula here because you're going to see in a second we have learned something very close to this before. And in fact, I'm going to put them side by side. So having discussed the electrical current, and again, close the switch, the current flows. It flows through the light bulb, and the filament is so thin that it heats up. It heats up, and it's enclosed here in the bulb, and it gives off light just based on how hot it is. But that means with the light bulb, we're actually in the realm of thermal physics that we've just studied, and we know there's energy and power associated with thermal physics. Okay, so we're going to tie this all together. Okay, so I'm going to erase everything, but I'm going to reuse this formula. In fact, I'm going to put it side by side with a familiar formula. And I hope I'm on 7. Okay. So electrical power. So electrical power, we would say power is equal to work over time. We know that's joules per second. That's watts. We're familiar with that. But we have Q delta V over T. And lo and behold, what is this but power is a current times a voltage, because this Q over T is just the amount of charge per time that's flowing. So the current I is equal to the flow rate of charge. Now, where have we heard of flow rate before? In our hydropower formula. So this is a chance to really get a nice comparison. So I'm going to put here, recall hydropower. Remember, there we had work was equal to mgh, and you had P was work over time was m over T times G times H. And this was the flow rate of water. Okay, flow rate of water in kilograms per second. Here we have the flow rate of charge in coulombs per second equals ampere. Okay, so we actually didn't have another name for kilograms per second, but the flow rate of charge is the ampere. Okay, but you'll notice these two formulas are exactly the same. I'm going to put them in a blue box just to put some color on board. Okay. These two formulas are very analogous, and underneath we're going to write P is equal to I delta V. This is one we're going to use a lot. But first I want to belabor the point here a bit, because this is too good to pass up on. Okay. So the power is the flow rate, and the of the charge times this voltage. And here we have the flow rate of the water times G times H. So we can see this G times H is what we could call a potential difference, just as we call this a potential difference. We could actually call this a gravitational potential difference. Although we didn't, and we won't adopt that, but that's what the analogy is. And you can see the higher the height here, G is constant here on Earth, right? But the higher the dam, the higher the penstock, the greater the altitude difference, you know, the more power we can get out of the same flow rate. And the same thing holds true the higher the voltage, right? Given the same current, the higher the voltage, the more power we can get. So it's a very nice analogy. We've worked with this one before, and all the skills that we have in dealing with this formula we get for this one as well. Easier, in fact, because yeah, we're usually not concerned about how many charges there are, which sometimes we did in terms of how much mass there was. We're just worried about the rate itself. Okay, so from here on out, I want to just focus on the electricity. This was the hydropower analogy that is so nice. And this is something that you have from your household life. Power is measured in watts. Current is measured in amps or amperes. And voltage is measured in volts. So I can write under this thing here, watts equals amps times volts. No need to ever forget that, right? Very, very basic. And so I have a good idea for a homework problem. And I'll go ahead and erase this. And this should be interesting if you go around your household and get a list of, you know, a good dozen appliances that you have. You know, in the bathroom, you've got the curling iron and the hair dryer and the electric toothbrush, if that's how you operate. There are light bulbs that you can find the wattage rating for. And I'll make a little list. You guys can make a better list. And I'll tell you why we want to do this. So what we want to do is find out how much current in amperes all of our various appliances draw. How much current do they require? So here's our homework project. We want a list of household appliances. And an example would be, you know, you've got a coffee grinder, you've got a toaster oven, you've got a hair dryer, etc. A good dozen. Look around, see what you've got. Light bulbs, or I'll just write light fixtures. Certain appliances, you look on the bottom, they've got a little tag with all of those data on it. Okay, so I have a coffee grinder. It says 200 watts, 120 volts, for example. Okay. So what we want to have is how many watts. Watts, capitalize the watts, how many watts for all of these, etc. And then how many amps? How many amps? Well, for that we have to know the voltage. And it turns out that the voltage, it's not like a battery, but it's 120. Okay, it's alternating current. We'll talk about those differences later, but right now the formulas are adequate. The formulas still work. So how many amps? And what we do there is we have delta V is equal to 120 volts for the household wiring, or delta V is equal to 240 volts. Now which one is it? Okay. The 240 volts is for an electric clothes dryer. It's for electric range, it's for the air conditioner unit on your roof. It's for the big appliances, but your standard household appliances, 120 volts, okay? 120 volts, so this is the one that's most important. Okay, so you can get a big list of those, and you'll find out how many amperes for each one, and that'll tell you how many can you plug into a wall outlet before you blow the circuit. That's something that everybody needs to know, and actually most people have experienced it at some point. So I'll put that information down as well. I can go ahead and erase this right here. So it's all up on one board. I can even keep numbering these things. So let's call this 8. Okay, and then I'll be up to 9. Okay, I'm going to put that formula up again. So 9, now that we know what this is, we have power equals current times voltage. So, and let's just do an example. I is equal to P divided by delta V. For example, if you had a 60 watt automobile headlights, 60 watts sounds reasonable, divided by 12 volts, you'd be looking at 5 amperes. That would be the example. So all of your household appliances are going to be divided by the 120 volts. Okay. And you'll get currents for those. And then here's the note I'm going to put here. The note is that your light circuits in your household now, so I'm talking about household electricity. Light circuit has a 15 amp circuit breaker. That means if there are more than 15 amps on your lights, you're gonna switch it off automatically. And the plug circuit, which could, in a house, it could run around a couple of bedrooms. It has 20 amp circuit breakers. So how many of those hair dryers that a lot of households have can you plug into one circuit? Okay, how many hair dryers can you plug into one circuit? So assuming that you guys have a hair dryer at home, how many amps for the hair dryer? This is an important one because it seems like all students have experienced that. Right, they have a roommate, they put 2 hair dryers in a circuit and blew the breaker. Okay, hair dryer. Okay, so this will be a good assignment. Get as many of these as you can, and then you'll have some understanding of what's going on there and how much amperage is being drawn, say, even at any one time. Okay, let's see how we're doing for time today. That's more than I intended. Okay, that's about 3/4 of an hour. Okay, let's see. Let's draw a resume of what we've done here. We've made it very systematically and principally into this power equals amps times volts formula. These are the wattages of everything you have running in your electrical life. These are the currents in amperes, and this is the voltage. So for your household, you've got 120 volts on the line. There's the normal plugs. Like I said, the dryer, the range and stuff, you have electricity, would be 240 volts, but those are different plugs, right? They're not standard plugs. And you want to have this list of these things here. And show me what you find, and when you take a picture of your notes, maybe focus in on whatever's interesting there on all of your appliances. And so once again, before I leave you, take good notes, take some pictures of them, send them to me, And we'll be in touch. I'm going to send you your exam scores back sometime this week. Shouldn't be too long. Okay, good. See you next time.